Okay, so let's move on now. So I'll start. So today I'm going to talk about mainly std PMR functionality in modern C++. So actually we're starting having this functionality in C++ 17 and some features of C++ 20, which could help to implement a very effective and expressive algorithms. So some traits of the new features which can be integrated in the code which we know and which we write. So factually, I'm going to tell you about some examples of sorting algorithms like merge sort and maybe other famous sorting algorithms like quick sort, and maybe we'll discuss some others. Those algorithms are going to illustrate what we can do with our new functionality like std-PMR and how we can write an expressive and safe code with C++ 20. So let's go. Let me tell you about myself. So actually, my name is Ivan, and currently I'm working as a quant analyst at Barclays. So I'm working in a credit department. So I'm doing credit instruments pricing like CDS, bonds. So actually, I'm helping traders with building credit trading tools like libraries and other stuff to price the instruments and to make successful trades. So actually to buy expensive and to sell low, to sell high. So actually my previous C++ experience lies in the fields of video processing, satellite image sharpening, and CUDA numerical simulations. In terms of video processing, I was doing some neural networks like YOLO V3 functionality to detect objects on frames and to do some pipeline stuff. And in terms of satellite image sharpening, I was doing panchromatic sharpening. It's a task where you can have a monochrome image of high resolution and also a small image of low resolution. And you need to combine them very fast and very effectively to make an image of high resolution and colorful, which should also be colorful. So it's a very famous and very important task in image processing when it comes to planes and satellites. It's normally being used by such companies like Google to provide Google Maps service with illustrations of the relief of the Earth and so on. So in terms of CUDA numerical simulations, I used to do some physics simulations, which is mainly called by n-body simulations tasks for high temperature physics and low temperature physics, so plasma physics and condensation problems. Some special effects is very difficult to model, so actually in the laboratory, and it's possible to model them numerically. So I did effective CUDA simulations in the starting of GPU era. So I was probably the first person with my scientific advisor to do these simulations. But let's move on to our today's talk, where I'm talking about std-PMR and the recent C++ features. So the agenda of our talk is I'll start with sorting algorithms. I'll refresh some basic facts about various sorting implementations, and I'll probably remind you some famous algorithms and some bits to compare them. So mainly I'll speak about quick sorting algorithms, merge sorting algorithm, and also I'll discuss in more detail the merge sort algorithms and mainly its implementation in canonical C++, which leverages std and place merge function of std library. So this function has a couple of drawbacks, and I'll discuss it later. And probably our main focus will be to replace this functionality with some stuff from std-PMR library. So I'll talk a little bit later about this in more details. Then we'll compare our implementation implementation, and those we've obtained and see earlier with benchmarks. Mainly I'll use Google benchmark, and we'll see how we can improve the speed of our code. We'll make the conclusions how everything works, how to use it, but factually I must notice that my presentation is more concentrated on familiarizing you with these features, but probably for production you'll need to implement a more performance, how to say it, a code with better performance and maybe more adaptive with some other stuff, leveraging modern functionality of central processes. So I'll just illustrate the library and how we can use it. So let's start. Sorting algorithms. Let me start from the fact that we have two complexities, time complexity and space complexity. Time complexity is being measured in the number of actions you need to do, and the space complexity is being measured as the memory, the amount of memory which you need to perform your algorithms. And so in terms of sorting algorithms, we have a developed theory which says that factually for common sorting algorithms, the best complexity is linear logarithmic complexity, which we can see on the slide here. So the most famous sorting algorithms with this log linear time complexity are heap sort, quick sort, and merge sort algorithms. Obviously, there are some others, but let's concentrate on those ones. And we won't consider less advanced and less sophisticated algorithms with quadratic complexity, because probably they are not very interesting for us. So let's concentrate on quick sort and merge sort, because they share the principle of divide and conquer to actually to make the actions. And let's start with quick sorting algorithms. It's probably the fast sorting algorithms, but it doesn't need additional space complexity. But the drawback of these algorithms is that in the worst case, their time complexity is quadratic. So actually, it appears when we have an unbalanced, let's say, tree, if we remember the algorithms, how the sort is being done. So actually, sometimes it can be very, how to say it, very slow if we have a very, very rare and special case. But sometimes it could happen. Merge sorting algorithms is more stable, but it requires more space complexity, more space to store intermediate results. It requires linear space to store elements. But the advantage of this algorithm is that time complexity is absolutely stable, and it's linear logarithmic. So actually, sometimes it's reasonable to use merge sort when you are not sure of the time, if you need the time complexity to be more stable, and you don't want to be risky to have a worst case of quick sorting algorithms. So actually, it's the main advantage of merge sort, but we more likely we use merge sort to illustrate our new features and how to use STD-PMR to implement it a little bit better than we could naively do with our basic canonical C++. So let's move on. Let's consider quick sorting algorithms. Here I presented the implementation of these algorithms, and we can see the function which takes two iterators, head and tail, and comparator to compare the elements in the container which we are going to use. So actually here I'm using new features of C++20 like bidirectional iterator, and also I'm giving the default value for comparator being std less from standard library. But obviously, if we want to use another algorithm, we can actually use something different if we need. So the implementation is rather canonical. If we have an empty container container, we do nothing. And then we take the last element of our container, and we are applying yesterday partition algorithm, which actually doesn't sort the elements, but it takes the pivot element and puts all the element which is less than pivot element on the left, and other elements put on the right. But the order of the left and right part are not sorted. So actually, we need to sort more to have a stable ordering. I mean, all the elements to be ordered. So actually, once we done the partitioning, we swap our last element, pivot element, with those which is on the pivot position to be it the lowest on the right part, and we apply a quick sort for the left part and for the right part. It's the principle divide and conquer. So actually we repeat it until the container, actually the array, is sorted, and once we've sorted it, the sorting finished. So it's a recursive function, and so it's basically can be presented as a tree if we want to think about it and to mentally visualize it in our head. So actually, hopefully it's a very famous algorithm and everybody knows what it's doing. And I just remind you the basic traits of the implementation we are going to compare and we are going to talk about later. So let's move on to merge sort. It's very similar and I would say a simple implementation. Here we also have C++ 20 features for iterator. We are going to use bidirectional iterator. Also, we can use a comparator with the default template parameter here. So, and we are going to write the similar function for merge sort, where we can pass two iterators, a head and tail iterator, and also a comparator, which is an optional argument. And we defaulted to std-less function from std library. So actually, we calculate the distance between head and tail, and we split our container or our array to two halves. So actually, we find the middle element, and we apply the merge sort, sorting actually recursively these halves of the container, and then we apply merge in place merge functionality, which merges both the parts. And once we've done it down, we starting merging, and we do it up. Actually having the order in our elements. Obviously, we need to do nothing if we have less than two elements. So if we have 0 elements, our container is simply empty and we don't need to sort it. And if we have only one value, we also don't need to sort it. I guess the algorithm is even simpler than a quick sort and easy to understand. So actually, it's probably a canonical version of these algorithms. And I'm going to talk a little bit about how to improve it in terms of speed and performance in C++. So actually, the main disadvantage of this implementation is using the function in place merge, which actually allocates some memory each time being invoked. So actually, here you can see the official documentation for this function, and actually those details which I need to talk about are that how it's being invoked. So actually, these two parts, we also, it's very important that the merge is stable, and actually that we can pass a comparator to these functions to customly compare the elements. But the main drawback is here that the function attempts to allocate a temporary buffer to making the merge procedure. So actually it allocates each time being invoked, which obviously not very well for performance, because allocation is a slow procedure. Probably we could optimize it, because actually we know that our containers initially have n elements, and we can allocate the memory for this number of elements once we're starting doing our sort. So actually we won't need a buffer more than for n elements, and it's our advantage. It's our knowledge which we can leverage when we are trying to use std-PMR. So let's move on to std-PMR. I'll tell you some very basic details about what it is, and then we'll see a couple of examples how we can leverage it to make our sort faster. So how we can improve our algorithm? We can use std-PMR functionality from the newest standard of C++, and actually there is actually a specialization of vector a vector. So actually we can use a polymorphic allocator instead of standard allocator from previous versions of C++ library. So PMR vector is it's a container which we are going to use in the next example, and it's the specialization of standard vector, which we know from the very beginning of C++ STL library, but with a special polymorphic allocator, which actually leverages so-called memory resource class. So it's we need to define, we are going to define std-PMR memory resource. We'll create a custom class which manages the memory we are going to use. So the idea will be to allocate the memory which we are going to use in the very beginning, and just to reuse this buffer, decreasing and increasing the count, the number of bytes which is being used in the buffer, depending on what stage of the our sorting algorithm we are currently on. So actually we are going to do this, we are going to start this with implementing custom merge memory resource, which is being inherited from std-PMR memory resource. So actually here we'll have a standard vector as a buffer, but we could also use another container, but probably the vector is obvious and the best solution for this. So actually, and we are going to make a counter for the number of bytes which we are going to allocate and deallocate. To create a custom resource, we actually need to override, mainly to override two functions, allocate and deallocate. And there are other functions, but actually I omit them for simplicity. So actually, deallocate normally being leveraged by polymorphic allocator, and it allocates memory for our resource. So we are going to allocate the buffer, which would be enough for each invoke of our sorting algorithms, no matter what's the number of elements we are currently sorting, half of array, even less, and maybe the full array when we are merging. So it's important. So actually here we account the number of bytes we are being used, and so actually we are then deallocating them using deallocate function once the procedure has been completed. So actually, I guess the functionality is more or less understandable and rather obvious. It's the simplest version which we can do. So actually, I don't think it's difficult to understand what's happening. So let's move on to a custom class, which is going to store the state mainly. So actually, before that, I created the functions, but now I guess the best implementation is to store the state of the resource. So actually, this has been done to store a merge memory resource inside it, and to deallocate it once the sorting procedure has been completed. So actually, we can see here bidirectional iterator, which is pretty similar to those we had for functions, and the comparator as a template parameter. So here I implemented a merge function, which takes the iterators, and actually it's very similar. It has very similar functionality for in-place merge from the standard version of STL library. So in the beginning of this function, we create a merge result. So actually, we allocate the number of bytes which we need to sort the part of our vector, and we should bear in mind that we have the buffer when we're actually creating this class. I'll show it a little bit later, to store all the numbers of our container. So actually, it's enough to allocate this memory resource once in the beginning when we constructing the class later, and to reuse the resource many times. So actually it won't allocate one by each time we are being invoked this function. It will reuse the memory. So it will be the main advantage of our implementation. So actually here is the standard merging procedure where we merge the numbers we have. And factually here, we call the sort method of our class. So factually, we do the same which we did earlier in merge sort function. We calculate the distance. If we have less than 2 elements, we simply don't have anything to sort. So we return the state we have, and then we apply the sorting procedure, but using a merge function, which we discussed earlier, and which has a constant permanent buffer which with enough memory to store all the elements or a part of elements, and then we put the result back. So actually here we have a constructor for merge sort, which mainly allocates the memory and puts the comparator into the right place, and actually an operator which just invokes sort method for the function. And our new function, a merge sort, factually creates the merge sorter class and allocates the enough memory for the buffer. So factually on this stage, in this line, we allocate the enough memory to store all the elements, and we sort them using this buffer, and not allocating the memory each time being invoke merge procedure. So it's the advantage. So probably let's move on to benchmarks and to see what we have. We will compare three main functions. So quick sort, merge sort, and later we'll compare merge sort and PMR merge sort with the faster performance, which leverages STD PMR functionality. So here we have, I use Google benchmark and pass the different number of random elements to sort. So actually, a quick sort here is being invoked with 8, 64, 512 elements, and so on. And there we can see the time which needs the algorithm to solve the container. So actually, the number of elements is being similar to all the cases we'll have, and we can compare actually the time which is needed for all the implementations and both the algorithms to sort elements, and we'll make the conclusions about the performance and what we achieved with this very simple improvement. So actually, quick sort, we can see that here, for example, let's compare merge sort and quick sort for 8 elements, and we can see that quick sort is obviously faster, and it's a very convenient result. It's theoretically quick sort should be faster, but it should have the same time complexity, and we can see this on our algorithm. So actually, quick sort is faster for 8 elements, for 64 elements, and so on, until the biggest number we can compare here. So actually, the next slide illustrates the comparison between merge sort and PMR merge sort. So the PMR version is the version for with improvement memory handling, which I demonstrated earlier. We can see that actually the timing is pretty similar for in the beginning. So for 8 elements, for 64 elements, but factually we can see that for some cases we have an improvement, but for other cases we have some disadvantages of timing. So actually it depends on cache locality and so on. But for the most cases, we can see that our PMR merge sorting algorithm is a little bit faster than the version which we do with merge sorting algorithms. So depends on the processor model and so on. We can see that the result can be normally faster, but sometimes it even can be slower, which is a bit surprising. This mainly happens when we're dealing with cache and so on, and it's a very interesting point to research for the future. But mainly the PMR version should be a little bit faster than those version for simple merge sort with canonical implementation of STD merge algorithms. So hopefully the talk was very interesting, and I'll be happy to answer your questions. Any questions? Okay, so thanks for the explanation. problem. Okay, let's finish it. And thanks for participating. Bye.